Hello and welcome to Electronics for Product Design. I will be taking you for the first 2 years of product design course, teaching you all the electronics and microcontroller stuff. Now my name is Paul Watts. I'm a software developer by trade. So I've worked for 20 plus years commercial industry, working in software development. Started off with music jukeboxes. These are the devices you used to have in pubs. You used to put the coins in, you select your music, you used to play it out on the main sound system. We don't tend to have them anymore because obviously music has moved on quite a bit since then. We've got it on our phones, we've got it on all sorts of other devices. People don't actually generally like paying for their music. So the jukebox industry kind of not died, but it's not great anymore. But back in the day, it used to be quite a big industry. In those days, we also used to, it was sort of the early days of the internet. So you used to have your dial-up modems and stuff like that. So I actually dealt with all that online stuff, downloading your music, all sorts of things to do with licensing and things like that. Once I did that, I then moved into contracting. So I went into individual companies, normally 3 to 6 months, sometimes a bit longer, as a specialist going in, essentially fixing their problems and solving their issues as they came up. Now, I worked for a couple of medical device companies. I've worked for Space Labs Healthcare. They were an ECG monitoring company. They'd have this little Eclipse device attached to your arm, have ECG pads on it, and it would read people's heart rates and heart monitoring, basically, over time. Now, what would happen with that is they'd have a mobile application. If you felt a little bit squiffy, if you felt a bit ill, you could press the button on the device and enter a diary log entry just explaining how you felt. A medical practitioner could then have a look at that data later on, and they could actually look at your diary, look at the events that you raised, and see if there was actually anything going on with your heart. So it's basic monitoring type stuff, but the device would run for maybe a week or so while they monitored you in your everyday life. Also worked for a company that did blood pooling. So that's the idea of taking a load of blood samples, pooling them all together, and doing a single test on that pooled blood. You can then test to see if you have a condition in there. Let's say you're testing for something like AIDS. You could test for AIDS in that whole sample with a single set of chemicals. If it all came back negative, then every single person in that pool was negative for AIDS. If you had a positive, what you'd then do is you'd split that sample down into smaller groups, and then you'd retest. The idea here is that you're not testing every individual sample, and therefore you are actually saving both time and money on that sampling process. Once I did that, I also worked for Next, which is a clothing company. Worked on their mobile application for about 3 months. I then moved on, and I actually worked for around about 2 years on and off for G4S subject tracking. They're a company that does the ankle tags and things like that. For monitoring people, maybe if they have ASBOs or if they commit criminal offences. They're not in prison, but we're just monitoring where they are, keeping them in the curfews and things like that. We also have victim protection on that as well, which keeps 2 people apart. So you've got your victim and your subject, and you want to keep them a certain distance apart. Should they ever get too close, the system will track that. They can send out an officer or call up the subject and ask them to move away. So it's all about sort of location tracking on individuals that we want to monitor. As part of all that as well, I also worked for Nottingham-Trent. That's how I actually ended up in the university on a project called FRAME, Facial Remote Activity Monitoring Eyewear. It's a pair of glasses that you'd wear if you had Bell's palsy. The idea with this was that you'd be able to rehabilitate yourself. So with Bell's palsy, you end up with paralysis of some of the muscles down typically one side of the face. Now, what we wanted to do with this was track, using the glasses, the muscle movements in the face, and then allow the person to essentially retrain those muscles so that they can get things like their smiles back and just get that kind of natural look back. That was all part of a mobile application that I worked on that connected to the glasses with one of our partners that we work with. And then we also had an online cloud platform where the specialists or the clinical specialists could log in and monitor the progress of their patients. Once that project came to an end, I then took on a little bit of lecturing. Since then, I've been working on and off until maybe 2 years ago when I took on this role full time, where I'm teaching electronics to product design students. Now, when it comes to microcontrollers, I've got, again, 20 plus years in microcontrollers. In all the different industries, I've worked in microcontrollers at some point or another. With jukeboxes, we looked at background music systems just using basic microcontrollers. And then in other industries, they wanted to use microcontrollers for monitoring type solutions, etc. So I've got plenty of experience in those microcontrollers. And then I've got the Arduino experience, obviously, actually teaching here at the university. I've then got loads of experience of actually aiding students. So when you go into your final year or even in your second year, you will probably have an idea. Now that idea will possibly rely on some electronics. Feel free to come down here, talk to myself, Sue or Matt, to ask or pass your ideas to us and see if we think it's a good idea or if we can give you a suggestion on how to do it. If you have any doubts or if you're uncertain about something, certainly related to electronics, just come down and just ask, and I'm sure we will help you as best we can. So let's start off with the real basics of electronics. We're not going to go into the complex physics. We're not going to go into any complex calculations or anything like that. You don't need to know that. You're not electrical engineers. What you need to know is the basics of circuits so that you can design and understand how to build basic circuits to show off your products. Okay. So the first thing we need to look at is the basics of a circuit or a power supply. Okay. Now a power supply is measured in volts and amps. The volts are effectively those little electrons that travel through the wires. Okay, now those little electrons will carry energy inside of them, and that energy is the amps. Okay, so each volt will carry a certain amount of energy. Now a volt can carry a varied amount of energy. Okay, it's not limited to the amount of energy it can carry. Okay, but the number of volts is typically limited by the number of electrons inside the power supply. Okay, so you can have a volt carrying any amount of current. Okay, but you're not going to increase or decrease your volts that often. Now, power supplies have a positive and a negative terminal. In the positive side, it's best to think of it as having the energy in the positive side. Okay. On the negative side, there's no energy. The negative side doesn't want any energy at all. All the electrons can float in that battery, but those electrons are quite greedy. They're going to want to pick up that energy. So what they're going to do is they're going to float around in the battery, and they're going to pick up the energy in the positive side of the battery. When they do that, they're going to have energy inside of them, and therefore they cannot go to the negative side because the negative side doesn't want any of that energy. Okay, so they kind of get stuck in the positive side of the battery. Now they're stuck there, it's waiting, there's potential energy, it's waiting for somewhere to go. The electrons can't move, so they're just stuck in that positive side. If we take a little piece of wire or a piece of metal that conducts electricity, and we connect it to the positive side and then to the negative side, now the electrons have somewhere to go. They can go through that wire. So what they will do is they will travel into that wire, they'll go through the wire toward the negative side of the battery. They will get to the negative side of the battery and they've still got the same problem they had before. Okay, they've got energy, they're not allowed inside the negative side of the battery. What can they do? The simplest thing they can actually do is simply get rid of their energy, and that is actually what they do. Okay, in this example, if we just take a wire, plug it into the positive side and then the negative side, we get effectively a short circuit. Now a short circuit is essentially wasted energy. Okay, what will happen is when they dump the energy out of those electrons, or those amps get dumped out, okay, it will heat up that wire. The more amps, the higher the temperature. Okay, so a high power, high amp battery will burn out that wire much quicker than a low amp battery. Okay, now once the electrons get rid of that energy, they can now enter the negative side of the battery. Okay, everything's happy. They go into the negative side of the battery, float around for a bit, cross over into the positive side, and because they're greedy, they grab some more energy. When they do that, they can no longer go into the negative side. Okay, so they now go through the wire again, all the way around, and repeat the process. Okay, so they go round and round and round, using up the energy inside of the battery as they go, burning it off in that wire in the form of heat. Eventually, that battery runs out of energy in the positive side. Okay, and so the electrons have nothing to pick up, they don't have anything to do anymore, and they just float around inside the battery with nothing to do. The circuit is now dead. The battery is dead, it's gone flat. Now with electronics, that's obviously not what we want. We don't want to just waste the energy. Okay, so what we can do is we can place components into our circuit with certain tasks. Okay, we can use the energy in a way that we need it to be used. Okay, so in this example, we're going to use a little LED. We'll look at LEDs a bit more closely in a minute. But an LED is essentially a light emitting diode. So when we put power into it, it's going to light up. Okay, now in this case, we're going to have a 2-volt LED. We're going to plug it into a 2-volt battery. And what will happen now is the electrons will leave the battery just like they did before. They'll go through the wire, but instead of just dumping their energy into the wire, we now have an LED that is going to use up that energy. Okay, so the energy will go into the LED. The LED will use up the energy in the form of light. It'll emit that light as it uses that energy. Electrons no longer have any energy. They go back into the negative side of the battery, go through, pick up some more energy, and go round and round, lighting up the LED as they go. Once the battery is dead, so there's no energy in the battery, obviously the LED will turn off and your circuit is now dead again. Now this is a perfect scenario with a 2-volt battery and a 2-volt LED. The problem that we have is it's very rare that you'll get exactly the right voltage for your LED or your circuit. This could be because you just don't have the battery available at the right voltage, or it could actually be that your circuit does multiple things. Some components will take 5 volts, some components might take 12 volts, okay? But your LED is still just a 2-volt LED. Okay, so you're going to need a higher voltage power supply to supply the other components, and then you need to drop down the voltage or the energy getting to the LED in order to protect the LED. Now, if we plug in a 9-volt battery into the LED only wants 2 volts. It's going to take 2 volts, but then there's another 7 volts of excess energy. That energy will still get dumped into the LED. Okay, but the LED doesn't want that energy. It's just going to get hotter and hotter and hotter as it absorbs that energy. Eventually, it's going to burn out. Now, in electronics, when we say things like eventually, we're talking very high speed, okay, nanoseconds, milliseconds, okay? So in this case, if you plug a 9-volt battery into this LED, it's going to get very hot, it's going to burn out, something inside the LED will melt, okay, and it will just cease to work, okay? It will break the circuit inside the LED will go off, and it is now dead, you can't use it anymore. So we burnt out the LED. We need some way of protecting the LED from these 9 volts, or at least the excess 7 volts. So what we're going to do is we're going to put in a little component called a resistor. Now, a resistor is pretty much designed for this task. Okay. Now, the resistor, in next week's session, we're going to look at how to calculate a resistor and how to understand the resistors. This week, we're just going to introduce a basic resistor. Okay. This resistor is going to absorb 7 volts worth of energy from the battery. Okay. That leaves 2 volts left to go into the LED. LED now lights up with those 2 remaining volts. LED lights up quite happily, and the resistor is absorbing the excess energy. Now, when it absorbs that excess energy, it is also emitting the heat that we would have seen coming off the LED, okay? But the resistor is designed for that, okay? And it will just dissipate that heat into the air. We're not saving any energy here, we're saving the LED, okay? And that is the basics of what we're going to use these resistors for today. We've got 9-volt batteries that we got in the packs. We're going to have a little 330 ohm resistor, I think, which is the closest we can get to the 350 that we need. And they're going to burn off the excess energy to protect the LEDs that we're going to put in our circuits. Now, just a quick overview of parallel circuits. You've probably done this at school, which is why I don't want to go too much into them. But the easiest way to think about a parallel circuit is we're using a single power supply, but we're creating multiple circuits. So we've got circuit number 1 at the top there. It's got a resistor and an LED. Comes out the positive side, into the resistor, into the LED, and then into the negative side. We then have a second circuit in parallel running off the same power supply, but it is a completely independent circuit. Okay, it's running down the way. So it's going to go down into the resistor, down to the LED, and then across and back into the negative. They are 2 separate circuits. Okay, we just call them parallel circuits because they're using the same power supply. Now, the most important thing to understand about any individual circuit is we always need to have a connection between the positive and the negative. Otherwise, the electrons simply cannot flow. They want to get from the positive side to the negative side, so we have to give them a path to go down to actually get there. So always remember when you're wiring up your circuits, you must have a positive side and a negative side connection. Otherwise, it just will not flow. So let's have a look at the first component that we're going to use today, and that is the LED or light emitting diode. Now, a diode is a component that only allows current to travel through it in one direction. Okay, so it matters which way round we place a diode. In the case of an LED, it's a light emitting diode. So it's still a diode, but what happens is when we place current into it, it lights up. Okay. Now, with that all in mind, we have to make sure that we actually plug the LED in the right way round, and the positive leg is the longer of the 2 legs on most LEDs. Okay. Now, if your LEDs have the same length leg, you can still look at those LEDs. If you look down upon the LED, you will realize that they're round for most of them, and then there's a little flat edge. Okay, that little flat edge is actually above the negative leg, or what we call the cathode. The anode is another word for positive, and the cathode is another word for negative. Okay. Now, it's important that we get them the right way around. Like I say, otherwise the current will not flow and the LED will not light up. They come in many different colours. So we've got your red, your greens, your blues, your yellows. Okay, but they only emit a certain colour. So they're designed to emit a certain frequency. We also get like infrared LEDs and ultraviolet LEDs. We can't visibly see those. But what they actually do is they can emit for your remote controls and stuff like that. They emit a very specific frequency, which is important because that saves us a lot of power. With the old fluorescent bulbs, for example, we've now replaced them with LED bulbs. The reason being that LEDs only emit certain frequencies, whereas the old fluorescent light bulbs used to emit many different frequencies. Many of those frequencies we couldn't even see, so they were kind of wasted, and that wasted energy. So the LEDs are very efficient at emitting very specific light colours. The next thing to look at is a resistor. Okay, we're going to give you a very specific resistor today that's going to work for the circuits. Next week, we're going to look at calculating resistors. We're going to look at how resistors work and how we can actually work out which resistor we have. Okay, they come in many different values. Okay, they're measured in ohms, from a single ohm all the way up to millions of ohms, so 1 mega ohm, for example. So they get into very high values, and there's lots and lots of different variants of resistors. Okay. It doesn't matter which way around we plug a resistor in. It doesn't actually care. It's going to do its job either way around. So there's not a positive and a negative leg. You can plug them in either way around. The value of a resistor is shown in the colour bands. Again, we will have a look at that next week, and we'll look at how we can calculate what the resistors are based upon those coloured bands. The next component we're going to look at is the tactile switch or button. Okay, now a switch is a pretty basic component. If you look at the diagram at the top there, that's actually the circuit diagram, but with an extra arrow on it. Okay, now with a switch, effectively the circuit is broken until we press down on the switch. If you look at the lever there, you'll see that that little lever is in the upward position, it's not connected, and therefore we have an incomplete circuit. The voltage cannot flow. When we push down on that switch, we're going to push that lever down, and it's going to make contact with the rest of the circuit. That completes the circuit, allowing the electrons to flow. That's a basic switch. Okay, we're just completing the circuit by essentially touching two bits of metal together. You can do the same thing with two little bits of wire. Okay, so we touch the wires together and you switch it on, release them, and you've switched it off. Okay, now the switches that we have in the lab for today's session, they're very basic button switches. We've got two different variants. We've got the 2-leg switch, which is the easiest of the switches. Okay, it goes into the breadboards very well, and if you can use those, use those. Okay. Now, they're just not in the diagram because we don't have those in the software that we use for developing the circuit diagrams for you to copy. Okay, but just replace that 4-pin switch that you see in the circuit diagram with these 2-leg ones. They're pretty basic. Now, the 4-leg ones are typically found on PCBs and circuit boards. Now, they actually have 4 legs, but they're in 2 sets of pairs. Okay, so if you look in the diagram in the bottom right there, you can see we've got pair A on the left and pair B on the right. They are effectively connected together permanently. Okay, there is just not a connection between pair A and pair B until we press the switch. Once we press the switch, the pair A is connected to pair B, completing the circuit. Okay, now it's just important that when you copy the circuit, that you copy it in the right way to ensure that you're connected to the right legs. If you're connected to both A, for example, then it will just turn on without the switch. If you're connected to both B, for example, it might not turn on at all. It all depends on how you've got it set up. Just make sure you copy the circuit diagram exactly as it is in the examples. Now, these things actually bridge perfectly over the gaps in one direction, so it's actually quite difficult to get them the wrong way around. Just bear in mind, when you push these into the breadboards, they're not always that reliable on the connection. You might have to push down quite firmly in order to activate them. Next component we need to look at is the breadboard. Now, the breadboard you may have used or you may not have used. You may have used it without understanding what you're doing with it. Okay, so we're just going to go into the basics of what a breadboard is. It's a reusable prototyping board. Now, what we mean by that is you can plug your or push your components into the holes on the breadboard without cutting the legs or without doing any permanent soldering. Okay, that means that we can actually pull those components back out again when we're done, and we can push new components in, or we can swap components around. Okay, we don't damage the components in the process, and we don't damage the breadboard. It's very useful for prototyping and quickly just sketching out our ideas, testing them, making sure we've got the right resistors, making sure the right components, etc. And then once we've done that prototyping stage, we can then go off and actually start making a more permanent version of it using something called strip board or matrix board, and maybe even a printed circuit board. Okay, but it's useful for the prototyping. It's useful for these early stages of projects. We also have jumper wires. These are the little wires that plug into it. You can use single core wire, or we can use the jumper wires that have pins automatically sort of crimped onto the end of them. We've got loads of them in the lab. Just bear in mind with the jumper wires that there are male to male connectors which have the pins on. We also have male to female where they have a pin on one end and a hole on the other end. We will use those in the future. We're not going to use them in the breadboards. Okay. And then we also have female to female, which are just holes on both ends. Okay, they are not broken jumper wires. Please don't throw them out. All you want in the labs for now are the male to male pin ones. If you come across the other ones, just put them back in the tray. Okay, and try to find a male to male. The other thing we can use with the breadboard as well, and we'll do that in the future, is IC or integrated circuit chips. Okay, but we'll look at that in the future. There is an area on the breadboard for that I'll show you in a moment. If you look at your breadboard, you will realize there is a red line and a blue line running down the vertical on both sides, so the left and the right. Okay, if we were to take the surface off, or take the case off the breadboard, you would see the following on the right hand side here. They are metal tracks. Okay, these metal tracks conduct electricity. So if we put electricity into one of the tracks, we can then pull the electricity off that track using another wire connected to the same track. Now, you'll notice that on the edges, the left and the right, where we got those blue and red lines, they are going in the vertical. In the middle area, you'll realize we've got 2 sets of horizontal lines. Okay, they are tracks running along the horizontal. Now, if we look first at the left and the right, where we've got those vertical lines, you will notice that you have a plus and a minus symbol next to those lines. Okay, they are intended for your power. We may be taking multiple power sources into multiple different parallel circuits. Okay, that means we need lots of these holes to provide power. That's why they run along that vertical, and there's lots of them. You'll notice that the red line and the blue line went all the way to the bottom. On some breadboards, there is a division in the middle where the red line and blue line stops briefly before then starting up again. That means that there's actually a break between those two areas. Okay, if you see one of them, if you have any questions, just let me know and I'll talk you through it. Okay, just bear in mind, if there is a break in that red or blue line, then there is a break in the copper track underneath the surface of the breadboard, and you're going to have to make a join yourself. Once we have done the power boards or rail areas, we then need to look at the center. This is where our actual components will be going. This is what we call the workspace area. It is divided into two sides. We've got side A and side B. Now, these areas are pretty much identical in their usage. They're just divided up by that central no connection bridge that's running right down the middle. Okay, that big dividing gap there is for our integrated circuit chips that we'll use in the future. Okay, with a chip, it's going to have, say, 8 legs on it. Okay, now one set of legs is going to go on the left hand side or side A, and one set of legs is going to go on side B. It's going to bridge over that gap. Now, we don't want the legs on side A connected to side B, hence the break down that no connection gap. Okay, but we do need to bear in mind when we're working with our components, when we're plugging our wires in, they're not connected across that gap there, and so we need to ensure we either place our components all one side, or that we just make sure we bridge over using the components. Okay, it'll make more sense as we use the breadboard. I just want you to bear in mind there is a side A and there is a side B. Remember as well that these ones are going to go in the horizontal axis. We don't need many connections for each individual component leg, okay, because normally we're connected in what we call series, so one after the other. Okay, which is why we only really have 5 holes. Some breadboards are a bit bigger, but generally speaking, each area or each set of connections only needs to be limited per component leg. Hence, we don't have so many, and then running in the horizontal. So that's the basics of the breadboards. I've now put up the exercise on the Now in the form of a PDF. If you have a look on there, okay, what I'm going to do is I'm going to come around, find out how experienced you are with electronics, how confident you are in electronics, and just get a general vibe for what everyone's like with the electronic side of stuff. Do the exercises, see how you get on. If you have any questions at all, just ask. I can explain things in a different way if necessary. If you want to know more of the physics side of stuff, by all means ask. But I am going to try and keep the physics as limited as possible while still being able to teach the electronics. But if you do want to know anything else, just ask and I'll try to answer as best I can. So you can find those exercises on the Now room. Log in on there, you'll find the PDF, follow the exercises, and let's see how we get on.